We talked about compounds versus mixtures and elements versus compounds. Most of the substances that we see in everyday life are compounds. They are not elements. Free elements, free atoms of elements are quite rare in nature. And to remind you, a compound is different from a mixture. Two important differences. The compound has elements combined in a fixed, definite proportion, always the same. In a mixture, the components can have any proportions. Like you can put a little bit of sugar in your tea or you can put a lot of sugar in your tea. It's a mixture. But you look at a compound such as water, and the ratio of hydrogen to oxygen is always the same. Here is a balloon filled with hydrogen and oxygen gas. That's a mixture of hydrogen and oxygen. You light a match to that and it's going to make a really nice loud sound. The first time I looked at this picture, I could not figure out what the heck that was a picture of. It's a picture of a water balloon that was just popped. And so the latex of the balloon is just peeling away and the water still has the shape of the balloon. It's really kind of a cool picture once you realize what you're looking at. This is a balloon filled also with hydrogen and oxygen, but they are combined in water molecules. Very different than this balloon filled with hydrogen and oxygen. Here, the ratio of oxygen to hydrogen is always the same. There are always 2 hydrogen atoms for every 1 oxygen atom. Over here, being a mixture, the proportions could be anything. You could have 1 hydrogen atom and all the rest oxygen. Or the other way around, 50-50, anything's possible. That's a mixture. So, a guy named Joseph Proust was the first to formally state this idea that elements combine in fixed proportions to form compounds. And this is now known as the law of constant composition. There's different ways to state it, but we can state it this way. All samples of a given compound have the same proportions of their constituent elements. A sample of water from the King's River that you purified and took any of the junk out, or a sample of water that you got from the middle of the Atlantic Ocean, or from the Nile River, or from Prince Charles's spit would have water in it, right? Anywhere you get water, it has the same composition. If we take a sample of water and decompose it, say by passing electricity through it, if we start with 18 grams of water, we'd end up with 16 grams of oxygen and 2 grams of hydrogen. Those are just example numbers. If you start with 18 grams, you'll get 16 and 2 grams every time. But what we're interested in is the ratio of the masses. So 16 grams of oxygen to 2 grams of hydrogen gives us a ratio of 8, or 8.0 to 1. No matter what size sample of water you decompose, the ratio of the mass of oxygen to the mass of hydrogen, always 8 to 1. And that's because compounds have constant composition. So let's look at this example. 2 samples of carbon monoxide obtained from different sources are decomposed into their constituent elements. One sample produces 4.5 grams of oxygen and 3.2 grams of carbon. So I'm going to write that down. 4.3 grams of oxygen, oxygen, 3.2 grams of carbon. And the other produces 7.5 grams of oxygen and 5.6 grams of carbon. Are these results consistent with the law of constant composition? You can't tell just by looking at the numbers. These samples were different sizes, so of course they're going to have different masses. We need to look at the ratios. I personally prefer ratios that end up being larger than 1. So let's look at the ratio of grams of oxygen to grams of carbon. So 4.3 grams of oxygen for every 3.2 grams of carbon. C. So 4.3 divided by 3.2 gives us 1.34. And then let's look at this one. Grams of oxygen to grams of carbon. 7.5 divided by 5.6, 1.34. The ratio is the same. The numbers themselves are different because one sample was larger, but the ratio is the same. So is this consistent with the idea of the law of constant composition? Yes, it is. The ratio of element masses in this sample and that sample are the same.